Hi guys, here's video 2-5 to be watched Tuesday 10-4. And the homework is going to be page 9, the entire thing. We are learning today the first shortcut to avoid having to use the limit definitions of the derivative. So all of the shortcuts that we learn, they're going to have, their names will be various rules. So today we're learning the power rule. And the power rule can be proven that it works using the limit definitions that we were using over the past 2 days. And it's much shorter. And those of you who are taking physics, I think already know it. So we're actually going to do, so this video lesson has 2 pages, pages 11 and 12 in the video packet. We're going to do page 12 first, actually. I think that'll have a more natural flow. So first I'll tell you what the power rule is, and then we're going to do like a bunch of exercises. And what we're looking to achieve here is speed. So we want to be like really fast with using these rules, but it will take some time. So some of you will probably go faster than me at a certain point, but I'm going to really break it down here on this page. So power rule exercises. So off in this margin, let's just say what the power rule is. So the power rule says this: if y equals ax to the n, okay, so this is a monomial. A and n are constants. So a is the coefficient, n is the exponent, x is the variable. So if y equals ax to the n, someone is jumping in the apartment above me. Oh my God. Okay, so I'm going to keep going. Then y prime equals a times n x to the n minus 1. All right, so notice what happened here. I took what was the exponent, I multiplied it by the coefficient, and then the exponent went down a power. All right, so I'm going to use this formula very carefully as we do these exercises. Some of you, especially if you've seen this before, you're going to be able to jump right to the derivative. Oh, and dy dx, guys, if you remember, that is Leibniz notation. So that's the same thing as y prime, which means the derivative, or the instantaneous rate of change, or the slope of the tangent line. All those 3 things, guys, mean the same thing. So yes. Alrighty, so our first example, we have x to the 10th. So this is of the form ax to the n, where a would be 1 in this case, n would be 10. So I can apply the power rule. And the power rule, by the way, only works in these situations where you have ax to the n. So the power rule works like this. I take the exponent and I bring it down in front, and then I subtract 1 from it. All right? So the derivative, if y is x to the 10th, the derivative of that, dy dx or y prime, is 10x to the 9th. Okay? The exponent came down, got multiplied by the coefficient, and the new exponent is 1 less than the old one. Alrighty, another power rule situation. Again, a would be 1, n would be 3 over 8. So 3 over 8 comes down, x to the 3 over 8 minus 1, which would be 8 over 8. So in the end, we get 3 over 8, x to the negative 5 over 8. Alrighty, so there's the derivative of x to the 3/8. X to the negative 2. And if you feel like you've got this, guys, I would speed up the video, go ahead of me, just check back to make sure we have the same thing. So the exponent comes down, and then we subtract 1 from it. So we get negative 2x to the negative 3. And guys, the goal is to be able to go right from there to there without doing the middle step. So if you feel like you're there already, then you can skip the middle step. Alrighty, then this next one, we have 3 times negative 1/2 times x to the negative 1/2 minus 1, which is 2 over 2. All right, now this is the first time that we're seeing in our examples a coefficient other than 1. It behaves the same way. Okay, I just move it out a little bit. I'm multiplying it by the exponent, subtracting 1 from the exponent. So this is negative 3 over 2 times x to the negative 3 over 2. Okay, so that is the derivative of that. And then this last one, I'm going to write down the coefficient. This gets multiplied by the exponent. I am subtracting 1 from the exponent. Negative 16 over 7 x to the negative 5. Okay? Now, so these were straightforward power rule situations. What we were taking the derivative of already looked like ax to the n. Now, these are not so straightforward, guys. These are not of the form ax to the n, but we can rewrite them in that form. So these are situations where you can use the power rule after converting to the form ax to the n. So this one, I can convert like this. This is the same thing as x to the 3/7. All right, so I convert from radical notation to exponential notation. Now I can apply the power rule. 3/7 x to the 3/7 minus 7/7, because minus 1. 3/7 x to the negative 4/7. Okay, here is another situation. I don't see right away that I can use the power rule, but then I ask myself, can this be converted to a power rule situation, ax to the n? And yes, it can if I make this observation. Okay, 1 over x to the 23rd is the same as x to the negative 23rd. And now I could use the power rule. So this is negative 23x to the negative 23 minus 1, negative 23x to the negative 24. Okay, here's another one. So this is like the previous two situations combined. We have a radical and a denominator. So I'm going to convert like this. This is x to the negative 1/5. So power rule, negative 1/5 x to the negative 1/5 minus 5 over 5. Negative 1/5 x to the negative 6/5. And one more. This can be converted into 11 x to the negative 1/7, and 11 times negative 1/7 x to the negative 1/7 minus 7/7, negative 11 over 7 x to the negative 8 over 7. Okay, guys, so there is a bunch of drills on the first page. That took almost 8 minutes, but hopefully you were able to speed it up because you got the hang of it and went a little bit faster than me. Okay, now on to a couple examples. So here are some power rule situations. Again, we're going to do a straightforward example, and then we're going to have to convert. So this straightforward example, okay, y equals that. I look at this and I see 4 terms. And each term in itself is of the form ax to the n. And when you're taking the derivative, guys, you taking a derivative of a full function like this with multiple terms is the same as taking the derivative of each term separately. So I'm going to go super slow here, guys. And again, you might be able to go a little bit faster than me, but I'm really going to break this down. So if I want to find y prime, which is the derivative of this entire function here that has 4 terms, what I want to do is I want to take the derivative of each term. So I'm going to introduce some new notation. So I'm going to do here 4 brackets, 1 for each term, okay? And especially if you've already learned the power rule, you might not find this necessary, but just try it with me and see if you like it. When things get more complicated, this will be super helpful. So outside of each bracket, I put a prime. This is a way of saying, the derivative of what's inside of it. Now I'm going to take each term and put it inside. Okay, so I would like you to do this with me for the notes, but in the future, you do not have to do it. And guys, I'm going to write 17 as 17 u to the 0. Okay, u to the 0 is just 1, and now I can see that a constant is in fact in the form of a variable to the n. So now I can apply the power rule separately to each of these. So I'm going to get y prime equals, okay, and guys, I'm going to try to go a little bit faster here. I'm not going to write out every little step. 4 gets multiplied by the 3, or 3 gets multiplied by the 4, so I got 12. 4 I subtract 1 from, so to the third, all right, plus 3 gets multiplied by 7 over 5, so I get 21 over 5. U to the 3 minus 1 is 2. All right, so this is the goal, guys, to be able to go faster. This is u to the first. All right, so 2 times 1 is 2, and then u to the 1 minus 1, that's u to the 0, which is 1, so this is just 2. And then this very last one, guys, the derivative of this, you'd get 17 times 0, which would make the entire thing 0. So the derivative of a constant is always going to be 0. In the future, guys, hopefully you won't even have to go through, you know, putting in a variable, raising it to the 0 power. You will just know in the future that the derivative of a constant is always 0. All right, so there's that. Okay. Now, here I have another situation where I have 4 terms to this function. I'm taking the derivative of it, and each term is not now in the form ax to the n, but they can all be rewritten that way. So I'm going to do the same thing I did before, and I'm going to set up 4 brackets with primes outside, which just signifies that I'm taking the derivative of what's inside. And to be honest, guys, I haven't seen this notation used a whole lot that I'm using here, but I did check with the workshop people this summer, and it's completely legit and awfully useful when things get more complicated, especially. Okay, so I'm going to put each term in the bracket, but I'm going to convert to ax to the n form. So this is 2x to the 3/7, 4x to the negative 5, 3/10 x to the negative 1/2, and then this is 4. And guys, if you want to go 4x to the 0, you can, but I'm just going to remember the fact that the derivative of a constant is 0, and then use it that way. Okay, so we get that y prime equals 2 times 3/7 is 6/7 times x to the 3/7 minus 7/7 is negative 4/7 minus 4 times negative 5 is negative 20, but we're subtracting it, so that's going to be plus 20 x to the negative 6th, because I subtracted 1 from negative 5. And then this next one, this is going to be plus 3/10 times negative 1/2. So I'm going to end up adding a negative number, so that's going to be a minus. 3/10 times 1/2 is 3 over 20, right? X to the negative 3/2, right? Because negative 1/2 minus 2/2. And then 0 at the end. So here we go, guys. I apologize if I made any arithmetic errors. Please let me know if I did. So that's that. Now, this is a rather, a relatively long video for me to be assigning a whole page for, except, the idea, guys, is that we want to get fast with this, and you don't get fast at something without doing a lot of them. So even though it is a whole page, I'm hoping it won't take you very long at all. And, I'm also hoping you were able to go faster than me at some of this. Alrighty, I will see you soon. Bye-bye.